Okay, welcome to lecture 26. It's chapter 6, section 5. This is all about periodic trends. Now that we know about electronic structure, we can explain a lot of patterns we see in the periodic table. And we're going to explain a few, some of which you have seen before, some of which you have not. So first off, we are going to start with something that's kind of a trend and kind of important for understanding the rest. We're going to go back to valence electrons. Okay. So here's your first trend. Lithium, sodium, potassium, rubidium, cesium, and francium. We're going to look at their electron configurations. Helium, 2s1. Neon, 3s1. Argon, 4s1. Krypton, 5s1. Xenon, 6s1. And radon, 7s1. These guys all have a single s electron as their valence electron. That is their outermost electron. Not only that, they all have the same sort of chemistry. These are all of the alkali metals. Similarly, for the alkaline earth, you have Ns2. N just being the energy level, or the row of the periodic table for that particular element. For the boron group, you have Ns2, Np1. The halogens are all Ns2, Np5. Yes, some of them have d electrons, some of them have f electrons. That doesn't really matter. What matters is the valence. And for the halogens, these are the valence, because their d and f subshells are all completely full, so they don't participate. Okay? The point is, every column on the periodic table has the same valence electrons. So we clear this off, and we draw our periodic table again. 1, 2, 3, 4, 5, 6, 7, 8. Remember the noble octet? You may have heard of that at some point. Oh, this is the noble gases. This is the halogens. These are the chalcogens, the oxygen group. These are the pnictogens. This is carbon, and this is boron. Okay. And then we have, the alkali and the alkaline earth. Okay. And we see similar patterns of behavior in the transition metals, even though they are a little bit more complicated because they have in S2, N-1 dx, but every column will have the same number of d electrons, and it will exhibit similar sorts of behavior. Such that, for example, you have copper, silver, and gold, all forming a column right here. Those are the coin metals, or the coinage metals, or the jewelry metals. Okay? Not only are they very pretty in a way that many other metals aren't, they're resistant to corrosion. They have very low reactivity. So you see column similarities there in the transition metals, and you also see they have the same number of valence electrons. So that's our first trend. For our second, I want to talk about something that it's not as useful in itself so much as that it's useful for explaining other trends in the periodic table, and that is effective nuclear charge. Okay, so for any given atom, we have, the nucleus. We have the core electrons. And then way over at the outside, we have the valence electrons. Now, the thing is, opposite charges attract, like charges repel. So these valence electrons are attracted to the nucleus, but they're repelled by the core. So there's kind of two different forces at play there. What this means is that the core acts as a shield, so that the valence electrons don't feel the full force of their attraction to the nucleus. So that's why we talk about effective nuclear charge. Okay? Because basically, they're seeing a smaller nucleus. Effective nuclear charge is actually a number, Z effective. Remember, just capital Z by itself is the number of protons. So Z effective is the number of protons that the core electrons, Z effective is equal to the number of protons the valence electrons see. Okay? So it's the number of protons minus the number of core electrons. The thing is, for a neutral atom, this is equal to the number of electrons. So in other words, the effective nuclear charge is equal to the number of valence electrons. So to put it another way, here you have your periodic table. Going from left to right, you have increasing effective nuclear charge. For every column, it's the same. But it increases from left to right because 1 valence, 2 valence, 3, 4, 5, 6, 7, 8, right? The transition metals, it's more complicated. We sort of leave that alone for the most part when we're talking about things like this. But this works very, very well for the principal block, for the primary block. Okay, that is to say S and P. Okay, and we use effective nuclear charge to explain a number of things. For example, here's our first thing we can explain using effective nuclear charge. Atomic radius. Now, electrons are kind of hard to nail down, and so the size of an atom isn't, a constant thing. But we can get a good approximation for the typical size of the atom. And there are various ways of doing this. But what we really care about is the results, right? So, the first trend we see should be obvious. Going from top to bottom, atomic radius increases. Okay? Every row equals new shell. Okay? You're going up to another energy level, a new shell. So every energy level is an energy level further away from the nucleus. Okay? So you get a big jump every time you go to a new row. So going from top to bottom, you're getting bigger. Now, what happens as you go from left to right? Okay, this is increasing effective nuclear charge. But if you're staying within the same row, what does that mean? Okay, you're staying within the same energy level, so they're the same distance out. Same distance, but greater effective nuclear charge, which means you're getting increased pull. there's an increased attraction between the nucleus and the valence electrons, the outermost electrons, which means smaller atoms. So, to put it another way, for atomic radius, try a simplified periodic table, the smallest atoms are in the upper right, the biggest atoms are in the lower left. Increasing atomic radius goes from top right to lower left. There are some odd exceptions here and there. For example, noble gases tend to be big because they're entirely core, but let's not worry too much about that. Okay? Just remember this trend. Big on the bottom left, small on the top right. By the way, this also explains ions. Non-metals gain electrons, and metals lose electrons, because non-metals have a high effective nuclear charge. Metals have low effective nuclear charge. Non-metals are small. It's easier for them to grab a hold of new electrons and pull them in. Metals tend to be big. It's easier for them to let go of electrons, for those electrons to escape and be pulled away by someone else. And speaking of ions, ionic radius. Ionic radius is similar to atomic radius, only we're talking about ions. So first off, we have cations and anions. Remember, cats make people happy. Cats are positive. And anions are negative. So cation means losing electrons. Anion means gaining electrons. So what is going on in terms of size? Well, it's really straightforward. You take something away, it gets smaller. You add something in, it gets bigger. Okay. So cations are smaller than the neutral atom. Anions are bigger than the neutral atom. Okay, you add electrons, you're getting bigger. Take away electrons, you're getting smaller. Booyah. But we can also do another interesting sort of comparison.